Hello, pre-calc honor students. Here we are with the binomial theorem and Pascal's triangle. And there's Blaise Pascal, born way back in 1623. And he came up with this amazing idea of how to use this triangle. And I'm sure you've seen this before, this Pascal's triangle, where you add up any two terms. So, like, if I take 6 and 4, I add them up and I get 10, the next term there. 21 and 35 is 56. 1 and 7 is 8, and so forth. So any two horizontally adjacent terms, you add them up and it forms the next term. Now this becomes very handy in many ways, and I want to give him full credit, but realize though that Qi Shen was a Chinese mathematician in the 14th century. That's like 1300s. Yes, well before our Blaise Pascal here, in a text called The Precious Mirror of the Four Elements. Okay, Chinese students, you can help me with those numbers later on. Let's expand these out. A plus 1 to the 0 is just plain 1. A plus b to the first is a plus b. A plus b squared, remember this, a squared plus 2ab plus b squared. And you can see the 1, 1, 1, 1, 2, 1 showing up from Pascal's triangle. Here's a cubed plus 3a squared b plus 3ab squared plus b cubed. And again, there's your 1, 3, 3, 1. Now for the next one, a to the fourth plus 4, notice the pattern there, 4, 1, 4, we got 4, 1 here, and this is a 6, because the vertical line is a 5, and then you add 1 to that. A to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. Okay, next row, a to the fifth, 1. Plus 5. 1, 2, 3, 4, 5. They snuck 5 into there. Okay. 5, a to the fourth, b. What's our next term? We have two ways to figure this out. We can look here. That's our symbol for 10. 10, 5, and 1. We can also add up these two successive terms, the consecutive terms. 10, a cubed b squared plus 10, a squared b cubed plus 5, a b to the fourth plus b to the fifth. And now a plus b to the sixth. A to the sixth, there's our 1. We've seen this symbol before, that's a 6. Plus 6a to the fourth b plus, look at this, a bar with 5 things on top of it. That looks like a 15 to me. And look at this, 2 10s is 20. See the 2 bars like that? 15, 6, and 1. So 6a to the fourth b plus 15a cubed b squared. Oopsie, we missed one. This was a to the fifth b. Yeah. And this is a to the fourth b squared plus 20 a cubed b cubed plus 15 a squared b to the fourth plus 6 a b to the fifth plus b to the sixth. Now I want you to see why in our binomial expansions this is matching Pascal's triangle, that same idea of adding two consecutive terms. If I come through here and multiply all these, if I do this longhand and multiply all these by b, I'll get a to the fifth b plus 5a to the fourth b squared plus 10a cubed b cubed plus 10a squared b to the fourth plus 5ab to the fifth plus b to the sixth. They're multiplying them all by b. Now I'm going to go through and multiply them all by a. When I do that, I get a times a to the fifth, so I get a to the sixth, plus a times 5a to the fourth b is 5a to the fifth b, plus 10a to the fourth b squared, plus 10a cubed b cubed, plus 5a squared b to the fourth, plus ab to the fifth. And you can see now, when we add these up, see how these like terms came from two different sources. The a to the fifth b term came from multiplying this one by b, but this one by a, and this first term by b. So to get the next term, that's why you add these two, the coefficients in front of these two, 1 and 5, to make 6, a to the fifth b, and so forth. Hopefully you see why Pascal's triangle works now. We can also find the sixth row of Pascal's triangle without knowing the first 5 by using combinations. This whole row of 1, 6, 15, 20, 15, 6, and 1, we got by going all the way down Pascal's triangle, but you can also do with combinations 6C0, 6C1, 6C2, 6C3, 6C4, 6C5, and 6C6, and you're back to 1 again. And you can also do it by multiplication. That is, 6C2 is 6 factorial over 2 factorial, 4 factorial. So a lot of this cancels out. It just becomes 6 times 5 when you do 6 factorial over 4 factorial over 2 times 1. And so another way is 6 times 5 times 4 over 3 times 2 times 1. And then 6 times 5 times 4 times 3 over 4 times 3 times 2 times 1. And then 6 times 5 times 4 times 3 times 2 over 5 times 4 times 3 times 2 times 1. And finally, we're just going to get 6 factorial over 6 factorial again and get 1. So this is a nice, this alternative approach is nice for just generating the first few terms in a row of Pascal's triangle. So here's the binomial theorem. If n is a positive integer, then a plus b to the n has many terms in it. It will have n plus 1 terms. And the powers on a will descend from a to the n all the way down to a to the 0. And the powers on b will come up from b to the 0 all the way up to b to the n. And we'll start off with nc0 and end up with ncn. So let's do the next term this. You'll get nc2, a to the n minus 2, b to the 2. And this will go on for a long time. And finally, our last term then is going to be ncn, a to the 0. The a will disappear, and b will be up to the n power. Equivalently, you could do this approach. And that is, say the next term here is going to be n times n minus 1 all over 2 times 1, a to the n minus 2 plus b squared, or times b squared, plus, let's do one more like this. That's n times n minus 1 times n minus 2 over 3 times 2 times 1. Oopsie. Too big an eraser, sorry. Let's try that again. N times n minus 1 times n minus 2 over 3 times 2 times 1, a to the n minus 3, b cubed, plus dot, 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 all the way to that last term, a to the 0, b to the n. And, of course, let's review our sigma notation on this. Probably the easiest way to write out the binomial theorem, because you don't do that dot, dot, dot in so many terms. You just list the one term in the summand. And let's use for our index here, I. So I will go from, and we actually want to start with 0, because notice we started with the b powers here, starting at 0. I equals 1 to n. And this will not give us n terms, but n plus 1 terms, because we're going from 0 to 1 and not 1 to n. NCI, that'll give us the coefficient from Pascal's triangle using combinations, times a to the n minus I, b to the I. So it's actually the second factor here, the second term in the expansion over here, that ends up going up in order from 0 up to n, whereas the powers on the first one descend. So there you go. There's your binomial theorem in sigma notation. Now example 1 here, give the first 4 terms in the expansion of x minus 2y to the 10th. Well, the first coefficient in Pascal's triangle is always 1. And then you've got the number of the row. And this is the 10th row, so it'll be 10. And then we'll go 10 times 9 over 2 times 1 for the next one. And then the fourth one will be 10 times 9 times 8 over 3 times 2 times 1. That's the coefficients. Now, and we just want the first 4 terms. Now we'll look at the powers on x. X is going to start with its highest possible power and keep on descending. X to the 9th, x to the 8th, x to the 7th. Now you know it's going to keep going, but they just want the first 4 terms. And then 2y, let's look at the powers on 2y. And I'm going to view it as negative 2y because this is plus the opposite of. So I start with negative 2y to the 0 power. So it actually doesn't show up there, but it shows up here, negative 2y to the first, then negative 2y to the second, and then negative 2y to the third. Okay? And then it's just a matter of simplifying the arithmetic on those, and you get our expansion over here. Let's just make sure we agree with this. There's our x to the 10th. Notice the second term is negative because the negative 2 times 10, there's your negative 20. 180 goes back to being positive because negative 2 squared is 4, and then you multiply it by, divide by 2, 18, there's the 180. And then negative 2 cubed is negative 8, so it goes back to being negative again. Now this problem is a little more tricky because you have to find a certain term in the row. In the expansion of a cubed minus 2 to the 10th, find the term containing a to the 18th. Well, a to the 18th, notice a is raised to the third already, so we have to think of a to the 18th as a cubed to the 6th. So when n equals 10 like this, we're going to have some term that has a cubed to the 6th, and so that leaves 4 powers left over, because the powers always have to add up to 10 out here. 4 powers left over for negative 2. So what's the coefficient in front? Well, you could spend a lot of time trying to figure out what order this is and so forth, but the easiest thing is just to put these two factorials underneath. 6 factorial to 4 factorial. And then, of course, it's n factorial or 10 factorial on top. Okay? Now, another thing to watch out when you're expanding terms is always do these powers first and then multiply by the coefficient into the powers. So 10 factorial over 6 factorial, 4 factorial, that's the one we've seen many times. That's 10c4 is 210. A to the 18th, 16. So now we take 210 times 16, and we get 3360. A to the 18th. Check. All right, flange out.